The sine and cosine functions are the building blocks for any continuous periodic function, no matter how complex. For this reason, we need to have a good idea about the properties of sines and cosines, since they can represent any continuous periodic function. This idea is embedded in the Fourier series, which we'll talk more about later. For now, we just want to refresh on the basic properties of sinusoidal functions. This is a plot of the sine function, and this is a plot of the cosine function. The definition of a periodic function is the function evaluated at x plus the period is equal to the function evaluated at x. So in this case, the function evaluated at 2 pi, the period of sine of x, is the same as the function evaluated at 0. The sine function is periodic, and one period is shown here. It extends infinitely many times to the right and also to the left. For sine of kx, we can find the period by taking 2 pi divided by k. That's found by setting kx equal to the period 2 pi and solving for x. The most general form of, for example, the cosine function is to write it this way: a constant times a cosine plus another constant b times x minus a third constant, and finally adding the constant d. In this case, the absolute value of a is the amplitude, so in this plot 1 is the amplitude. B gives the period as 2 pi divided by b, and c is the horizontal shift or phase shift. D is the vertical shift. I'll demonstrate all of these things in a moment. This is a Maple app that demonstrates the generation of a cosine curve or a sinusoid. The cosine is the adjacent side in a right triangle where this is 90 degrees or pi over 2 divided by the hypotenuse. The sine is the opposite side divided by the hypotenuse. Now if we have a unit circle of radius 1, the hypotenuse is always 1. So the unit circle, the length shown here in red, is the cosine of the angle that's being traversed as shown here. At 0 degrees, the cosine has a maximum length of 1 shown here, but it decreases quickly as the point travels around the circle and its value becomes a negative 1 or maximum value at pi, and then it returns back to 1 when this angle is 360 degrees. Now I've reset these constants back to a equals 1, b equals 1, and the rest 0, so that this general form of the cosine function is just cosine x. And here it's plotted, as we saw before, 2 periods. Now I want to show you the effect of the phase shift. If I take the value of c to be pi over 2, what I'm going to do is shift this right by pi over 2, so this point on the curve will move over to 0, and it should end up being a sine curve. So let's do that. And you can see this now is exactly the same as the sine curve. In fact, the Maple software, which is a computer algebra system, shows that this is in fact the sine of x. Just to reinforce some of these ideas, let's show a few animations. So I'll run this one, and what we're doing here is I'm multiplying this frequency factor times theta. Here I called it theta instead of x, but it doesn't matter what the variable is. Let's look at what the effect is. I'm changing k from 1 to 30, so I'm going to end up having 30 sine waves as k changes. Here's the value of k listed, and you can see the frequency changes. In the next one, what I'm doing is changing the phase angle. So as I increase k from 0 to 2 pi, that means I'm going to shift this curve to the right by 1 period. So let's run the animation. And indeed, it shifted exactly 2 pi to the right. Notice that when k is positive, the curve goes to the right. We write the minus k to make it turn out so that a positive k shifts right. And if you put a negative value in here for k, that would be theta plus the absolute value of k, and that would give you a left shift. That's just convention. In the next one, here we're changing the amplitude of the sine, so that should just cause it to grow. So that factor in the front, k times sine or cosine, just magnifies the amplitude. And in the last animation, we're going to subtract k from the function, and that's just a shift. So it's going from 0 to 5. It should shift this average point of 0 down to -5. So what's the look for? What's so amazing? The amazing point is that the sum of any number of sinusoids with the same frequency is that the resulting sinusoid differs only in the amplitude and phase shift, but it is still a sinusoid of the same frequency. This has far-reaching implications and is a characteristic of linear systems. For example, if I put a sinusoidal wave signal into an electrical black box filled with various components, I will get out the same signal, just modified in amplitude and phase, unless a special effort is made to change the frequency. What happens if I sum sinusoids of different frequencies? Let's look at a few plots to reinforce the ideas we just talked about. We'll start with a sine function, sine of x, and range it over -2 pi to 2 pi, so over 2 periods, as a point of reference. Now here I'm taking a sine of x and a cosine of x with scalars multiplying the amplitude. When I plot that, we see that it has the same shape. Of course, the amplitude has changed and it's shifted a little bit to the left here, but the shape is essentially the same, so it's a sinusoid. That's a pretty amazing fact. Now let's make this more complicated. We take the same two terms we had before, but I'm going to add a sine term that has a phase shift in it here, and another term, a cosine term, with another phase shift, and we'll do it over the same range. So let me plot this. Interestingly, it's a sinusoid again. It has a different amplitude and phase shift, but nonetheless it's a sinusoid. Now, what do you think will happen here? This is a sine of x, but this cosine term has a change in frequency. The frequency is doubled. Let's plot that. It's no longer a sinusoid, and that nice property of being a sinusoid is lost as soon as the frequency changes in one of the terms. But that nice property gives way to another property that's even more important, and that's the idea of the Fourier series, where we can approximate any continuous periodic function with a Fourier series, which we'll demonstrate a little bit later. I want to provide a few additional comments related to period and frequency. First, I favor radians as a unit of angular measurement because it is a naturally constructed measure. A radian is the ratio of the length of the radius to the circumference of a circle. For a unit circle, the radius is 1 and the circumference is 2 pi. So 2 pi radians is the angular measure of the circumference, which is also the period for the unit circle. Degrees can be used, but they are an arbitrary measure of angle. Most textbooks designate the period by t, but I have used p. The sine function is often written as shown with a constant k, but sometimes with omega. They mean the same thing, but omega is called the angular frequency because when omega is equal to 2 pi, then 1 period has elapsed. Think of k or omega as to how many radians per second are occurring if the sinusoid is describing a time domain function. You can see in this formula that if you want to write a sinusoid in terms of frequency, you can substitute 2 pi f for k or omega. The frequency is how many cycles per second there are, which are also called hertz. Finally, we can summarize. Writing a sinusoid with 4 constants, as shown, gives easy interpretation. The absolute value of A is the amplitude. B is the angular frequency or frequency factor. C is the phase shift. And D is just a vertical shift. Next, we can combine sinusoids. As long as they have the same frequency, then any number can be added together and the resulting sum will still be a sinusoid with the same frequency, but the amplitude and phase shift will be different. Finally, the Fourier series is written this way, which means that there is an infinite number of sinusoids of frequency 1x, 2x, 3x out to infinity. This is what allows for approximating any periodic continuous function by a series, which we demonstrate next.